well, a paper.
And then, yeah.
This generalizes a paper of 1992 by Pukhlikov and Khovanskii. So I'll quote them a lot today. And to begin with, well, let me present you an very general algebraic construction, which won't involve any like algebraic geometry or whatever, but well, this well, that's something you can explain to, I don't know, second year student. So I will construct an algebra starting from a homogeneous polynomial in n variables. So suppose I have a polynomial, a homogeneous polynomial f on an n-dimensional, let's say, real space. Well, R doesn't matter here. I can replace it by any field of characteristic 0, but well, I'm going to write partial derivatives, so I prefer to stick with R, and well, that really doesn't matter because everything is going to be polynomial. So if you like working over Q or even over Z, things will mostly work without change. So so let me start with a with such a polynomial. And starting from a polynomial, I'm going to construct an algebra, which I denote A sub f. For this, let me take the ring of differential operators with constant coefficients on my n-dimensional space. So these are some polynomials in these variables, d over dx1, etc., d over dxn. Well, and I would like to emphasize that these guys are differential operators with constant coefficients. So things like, I don't know, x I d over dxj does not live there. So I'm not allowed to multiply them by functions. I'm only taking scalars. And so this is my ring of differential operators. This is a commutative algebra, as opposed to, well, to this algebra I have, right? And I can, having a polynomial f, I can take all possible differential operators which annihilate it. So the annihilator of f is just the set of all these such that d applied to f is identically 0. So you see, this is an ideal. So if you apply d to f and get 0, then you can apply d times something and get 0 as well. So yeah, and of course it's a vector space. So this is indeed an ideal. And this is an ideal, actually a finite codimension. So the quotient of this ring over the annihilator is, well, for a polynomial, this is a finite dimensional vector space. Why is it so? Because if well, the polynomial has a degree, and if I apply some differential operator of larger degree to f, I'll get identically 0, right? So for d of degree large enough, well, these d's will lie in my annihilator. And also everything, well, let me just formulate a couple of facts about AF. So this ring is graded, first of all, because, well, everything has a degree. Well, my differential operators are graded, and my F is homogeneous. So, well, you can say that this ring has a grading, and as I explained 2 minutes ago, this grading is finite. And the upper component, A sub f upper d, is of degree equal to the degree of f, right? Okay, and well, and in particular, this this space is a space of constants, right? And I'm claiming that, well, this is my second property, that my top degree component is one-dimensional as well. Why is it so? Well, because of course this every time you apply a differential operator of degree d to f of the same degree, you get a number. And well, the homomorphism theorem or any the other basic algebra fact tells you that this is this image of AF D, this thing is at most one-dimensional, so you get number. These classes are indexed by numbers, and you only need to find out why it is actually R but not 0. But for this, you can say that for every homogeneous polynomial, you can find a differential operator not of the same degree, not annihilating it, right? So you can get a non-zero constant. Well, this is easy, right? So this means that these components are the top component and the zero component are kind of dual. And actually, there is a duality in other components as well. So this is my third fact, that AF satisfies something we call the Poincare duality, like the Poincare duality you have in the cohomology rings. So this works as follows: having two differential operators of total degree d, so one is of degree k and the other is of degree d minus k, you can cook up a number just by multiplying them and applying them to this f. You'll get a number. Well, eventually you may get 0, but maybe not. It doesn't matter much. So this is a bilinear map from a f to the degree k times af degree d minus k to f d, which is, as we know, nothing but the real numbers, right? So and this pairing is, this is a symmetric bilinear form, and this pairing is obviously non-degenerate. Why? Because if you apply some operator A to f, you get some polynomial of degree d minus k, and then you apply b. And for each a, you may find a b such that the result will be non-zero, such that ab applied to f will be non-zero. Right, so this is indeed a non-degenerate symmetric bilinear form. So in particular, it gives you an isomorphism between these two spaces. In particular, they have the same degree. So this thing is kind of symmetric. So they're the dimensions of these guys are from a palindrome. And the last thing I would like to point out is that this ring is generated by its first degree component. Well, this is easy because this is generated by the first degree component, and the grading is inherited from this ring. Well, so there are 4 facts about rings of this type. So starting from a homogeneous polynomial, I construct a ring with these properties. Everything clear so far? Okay, so I'll transfer this to the next slide and formulate a theorem, which is, the origin of this theorem is kind of obscure because, I think the people usually refer to Pukhlikov and Khovanskii, but in their papers, it is not, it is somehow written between the lines. And in this form, it was formulated by Khovanskii student Kiumars Kaveh in his paper of 2011. But anyway, the statement is pretty much obvious. So the statement is as follows. So that these four properties define such a ring. Namely, if you have a ring satisfying 1, 2, 3, and 4, then it has, well, then there is a polynomial on its first degree component such that A is isomorphic to A sub F. And this polynomial is just sending the first degree component into its dth power, where d is the depth of the grading of A, the number of graded components minus 1. So I'll say it again. If you have an algebra with such properties, graded with a Poincare duality and generated by the first degree component, then it has the form of A sub F for a suitable polynomial F. Right? Okay. And well, I already mentioned a couple of times that well, this was an abstract algebraic construction, but that's how cohomology rings of various smooth varieties actually look like. They do have grading, they do have Poincare duality, but the point is they do not necessarily have this property. They are not necessarily generated by the degree 1 component, but for some, especially nice varieties, this is true. So in particular for those varieties I mentioned in my in the title, this is true, and for toric varieties and flat varieties.
Женя,
Questions?
question.
Yeah.
So this property number 4, is it for any polynomial or for some special?
No. I mean that you can write down this explicit polynomial. Yeah. So then the statement is as follows: there exists an F such that A is isomorphic to A sub F, namely differential operators modulo the annihilator of F.
Mm-hmm.
And for F, you can take this polynomial.
No, I'm just thinking that if we just take arbitrary polynomials, then AF1 is basically full dimensional, right? Or not?
Well, you can take so you take a polynomial of, so you won't mod out by A of 1, you're saying.
Mm-hmm.
Well, this is true, but what happens to the higher components? No, you cannot take just an arbitrary one. Well, at least the degree must be as prescribed, right?
Okay.
To get something of dimension d. So, no, this is not just any polynomial. Well, of course, all the polynomials might work, but well, this one certainly does. Okay. Oops, sorry, there's something strange happening with the laser pointer when I'm trying to write things on the slides. So, well, let me just recall some definitions of the cohomology of toric varieties. And Dima, as I promised, you asked me to make the first 15 minutes clear.
Yes,
are you fine with that? So,
yeah.
Okay, so let me take well, for toric varieties in my talk will be always projective and even polarized, namely with with a given embedding to a projective space. So a projective variety living in a projective space of some bigger dimension. So how to define them? Well, the thing is that toric varieties are defined as well normal varieties with an action of an algebraic torus. Algebraic torus is just the multiplicative group of C to the power of D, well, some power, and I'm considering varieties with an action of this torus such that T has an open dense orbit on Y sigma, whatever sigma is. So I'm defining them so far as varieties with as torus embeddings, basically. You can think of this action as of an embedding. So well, you have a variety in a projective space. You have an action of T on your variety, and well, with an open orbit. And then you can say quite a lot of stuff about this. So, namely, everything is governed by a certain fan. So fan is a union of cones which cover, well, in my case, I want all rays of this fan to be rational. Sigma lives in Q to the power D, and well, there are rays of this cone. There are cones of bigger dimension. Well, and this the faces of this fan are in bijective correspondence with the T orbits of my variety, and this bijective correspondence inverses inclusions, like inclusions of closures, and inverses dimensions, namely cones of codimension, cones of dimension I correspond to T orbits of dimension D minus I. So, and well, maybe I'm too sketchy here. Maybe let me give you one or two examples. So suppose you have a cone, a subdivision of your plane into 3 parts. Well, 3 rays and 3 two-dimensional cones between them. So this corresponds to the projective space P2, well, embedded into itself, right? So, and I act by T1, T2 on acting on homogeneous coordinates. So let's say T1, T2 applied to X, Y, Z is, well, let me say, so let me say I multiply one coordinate by T1 and the other by T2. So T1, X, T2, Y, let's say Z. And in this case, I can take any point of P2 with non-zero coordinates into any other point of P2 with non-zero coordinates, just multiplying them by suitable T1 and T2, and I define them up to proportionality. So I can multiply them simultaneously by some scalar. So I have an open piece in P2, and I find chart where well, like, I don't know, big cell where all coordinates are non-zero, and then you have three adjacent arrays. Well, then you have, like, what does P2 look like? It looks like this, basically. So there are three lines defined by the equations x is 0, y is 0, and z is 0. And then there are three intersection points of these lines. So you see these lines, in fact, they are going to correspond to these rays on my picture. These t-stable points are these two-dimensional cones, and there is one big cell corresponding to the origin. So this is the correspondence. And I can say even more that I can draw a say a polytope taking some rational points on these lines and taking orthogonal spaces. So let me say integer points on my polytope. Well, I'll have a couple of points here. So this is the origin. And what if I take, I don't know, weights of these corresponding to these points? This is T1, T2, T2, well, T1 to the power 0, T1 inverse T2, etc. So this is 1, this is just T1, and so on. So, well, this gives me an embedding of my torus T1, T2 into, well, in this case, this is a 10-dimensional space of homogeneous coordinates. This is P9. So this is P2 embedded to P9. And, well, the image, well, yeah, sorry. So this is my torus embedded into C star squared embedded into P9, and the closure of the orbit corresponding to all ones, so T and T, if T corresponds to, if T, sorry, T, if I apply T to the point with all ones, and close it, take the algebraic, take the closure of this orbit, then I'll get something isomorphic to P2, namely the third Veronese embedding in this case. So anyway, just the bottom line is that toric varieties with an action of torus, are very nice objects from the point of view of combinatorics. They're, well, all the geometry you can ask about them actually sits in some combinatorial picture. This picture, well, can be a fan, or if you consider toric varieties with a given embedding, this is a integer polytope. I'll get back to that in a couple of minutes. And so, well, this combinatorial picture knows quite a lot about geometry. So, yeah, in particular, as I mentioned, the T invariant divisors, the T invariant subvarieties of codimension 1 correspond to the rays of this fan. And well, and you can ask yourself, what is the cohomology ring of this thing? So this is this cohomology ring as a vector space is generated by the closures of T orbits. So, well, you can speak about cohomology or the Chow ring that, well, like subvarieties up to algebraic equivalence, right? So well, this is quite the same thing. If your variety is smooth, and I'm considering smooth varieties, and so its cohomology ring is a graded commutative algebra, well, with a Poincare duality, and in particular, it is generated by the first degree component. Well, here I write the H2 because I'm dealing with complex varieties, and they form their cohomology rings form from commutative algebras, not supercommutative ones. And so the second cohomology ring is like there's nothing in the odd components. So H2 is, well, basically the first component, and it is generated by the first component because, well, every t orbit is, every cone is obtained as the span of certain rays of your cone. So every t orbit closure is obtained as the intersection of certain t invariant divisors. So, so the previous construction, so I can apply the previous construction that A star of y sigma is the ring of differential operators on the H2, on the, well, Picard group, modulo the annihilator of this polynomial, which maps a divisor to its dth degree. So a divisor is a subvariety of codimension 1. So if you take an intersection of d such subvarieties, I mean that you need to take certain equivalents to make them transversal, but at the end of the day, you intersect d subvarieties of codimension 1 in a d-dimensional variety, you get a bunch of points, and the number of these points is a number which you assign to this d. Sorry. Okay, so you have the differential operators on H2 modulo such a polynomial, and yes, and now comes another magic ingredient of the story. This is the Bernstein-Kushnirenko-Khovanskii theorem, or just Bernstein-Kushnirenko theorem. And this result allows you to compute the index of self-intersection of a divisor on a toric variety. So suppose we take some t-invariant divisor. This is a formal combination of t-invariant subvarieties of codimension 1 with prime divisors. Hi are just numbers, well, real integer as you prefer. And I already told you that these rows, rays of my cone correspond to a divisor, dh. And now let me, well, given a bunch of numbers, so on each ray I can write a number, and given such a picture, I can draw a polytope. How do I do that? I need to take the distance hi on each ray and take the hyperplane perpendicular to ri and intersecting it at this point. Well, so this distance must be hi, and, well, eventually I get a polytope, or maybe not if I'm not so lucky. So let me give you a quick example. Suppose that my H1 is pretty big and my H2, my H2s are the same, so I'll get something like this. You see, I'm running out of screen space, but you see what I mean. So so you don't get an actual polytope. You get something with self-intersections and something quite nasty. So in some cases you get a polytope. Okay. And actually, you can take the space these polytopes live in. Namely, you can take these h's as the coordinates on your space and say that, well, if you're lucky, they define a polytope. And if not, well, we can still consider the divisor, we can still consider the self-intersection number. And a theorem by Gorenstein, and Khovanskii tells you that the self-intersection number of the divisor, so this must be not n, but d. So this self-intersection number is also d factorial times the volume of my polytope, if it is a polytope. And if not, well, I don't have a polytope, but still I have some construction giving me a number, a volume of something I call a virtual polytope. This construction can be described in various ways. Like you can, if you like geometry, you can say that you define such a bad thing like polytope, and you're saying that the area of this polytope is, so you need to take the white area and subtract the red one. But well, I don't recommend it to do it in dimension n. So it's quite it's not so amusing. So I prefer to say that my actual polytopes form a cone of maximal degree in the space with these coordinates. And on a cone, you have a polynomial, an actual polynomial, and you can extend it to the whole space. So this will be your volume polynomial. So, and this is my construction of virtual polytopes with a span. So this is just a vector space with these coordinates and with volume defined on the cone of actual polytopes. And so a magical theorem tells you that the number, the self-intersection number, well, the number of solutions of a certain system of equations is just the volume of this polytope, right? So together with the previous theorem, we get a result by Pukhlikov and Khovanskii that the cohomology ring of a toric variety is isomorphic to differential operators on the space of polytopes with a span sigma modulo the annihilator of the volume polytope. Okay, so let me give you a quick example. So suppose we have a Pn, and in this picture I have P2. I have 3 lines. And so suppose I take n lines, which are just not lines, but rather arrays, but that are just positive rays, and they're sum within minus sign, like the ray of formed by vectors with negative coordinates, alpha, etc., where alpha is negative. So you have such a thing, and if you take the corresponding polytope, it will be a simplex, and you can compute the area of a simplex. So this is, well, the volume of a simplex is the length of its edge to the power equal to the dimension of the simplex, divided by the factorial, but we don't care much about the constants. So you need to, well, as this theorem says, you need to take the ring of differential operators in one variable, d over dx. So the simplest is defined by one constant, but it's by the length of its edge. So d over dx modulo the annihilator of the volume polytope, which is x to the power n, well, times some constant I don't care about. And these are exactly the polynomials truncated by the ideal of polynomials of, well, homogeneous polynomials of degree at least n minus 1. So the cohomology ring of the projective space has one generator in every degree up to the degree of the projective space itself. Well, so that's how this theorem works in the most basic case. Okay, and that's what we intended to generalize. And generalization of this story is, I think, so we wanted to pass from the cohomology ring to K-theory. I'll give you a very brief introduction to K-theory a little bit later, maybe in 5 minutes. And before, well, let me follow the same plan and present the algebraic construction, which we will get as the answer. So our goal is now to define the Grothendieck, to describe the Grothendieck ring of toric varieties in similar terms, and this is done as follows. So I started with a function on, well, I started with a polynomial on a vector space, but let me now take a lattice and take an arbitrary function on this lattice. Lattice is just z to the power something, to the power d. Well, so first, abstract algebraic definition. Suppose A is a commutative algebra with identity, and I have a linear function on this commutative algebra. So to any element of A, I assign a number in a linear way, and then I can say that I have a symmetric bilinear pairing on my algebra, namely to take the bracket of two elements, you need to multiply them and apply L. Well, I'd like to emphasize that in this case, A is, I don't require A to be graded. This is just an arbitrary commutative algebra with identity. So, and well, out of all bilinear forms, we like the non-degenerate forms the most. So let me say that I call my pairing defined by a function L Gorenstein duality pairing if it is non-degenerate. And you see, this is a generalization of Poincare duality. So if your algebra is graded, and so you have the top component of degree 1, then you have a pairing saying that you need to multiply two elements, and if you get a top degree component, then you take the corresponding coefficient. So the volume, in a sense. So, well, our first goal was to obtain a construction of such algebras, generalizing the Pukhlikov-Khovanskii construction. So, yeah, and that's what we found. So let us start with a lattice z to the power d, and I take a function on my lattice. Well, function means arbitrary function. That means that in every point of my lattice, I have a number. So this is just a function. So then I can act on these functions by shifts. Namely, I can just take the whole lattice and shift it by 1 and get a new function. So instead of g of x, I get g of x minus ui, where ui is the ith basis vector. Or I can take the ti inverse, shift it to the opposite side along the ith basis vector. So I have an algebra of shifts, an algebra generated by these ti to the power plus minus 1. So this is this is basically the group algebra of my lattice acting on functions on it. And well, again, I can start with any function, and I can take its annihilator in the algebra of shifts. So its annihilator, well, it's just the set of all combinations of shifts such that make it vanish. Well, for instance, if I have if g is a constant, then, well, I can shift it to an arbitrary direction and subtract it from the original function and get 0. So this means that my annihilator will be generated by something like 1 minus ti to the power plus minus 1. Or if my function is, say, linear, I can shift it, subtract it from the original one, and get a constant, which I know how to annihilate. So, well, same works with polynomials, same works with exponentials and quasi-polynomials. So you see that in some interesting cases, you get an interesting annihilator. In particular, if g is a polynomial, then this annihilator is a full codimension of is a finite codimension. So g polynomial, and then the annihilator of g is a finite codimension, just like it worked with differential operators. So when you have a lattice, you have shifts, not differential operators. So yeah, and you can mod out the algebra of shifts by this annihilator of g and get something we call A of g. So for a polynomial, this will be an Artinian algebra, finite dimensional one. So here's our result, that this algebra has Gorenstein duality pairing defined by evaluating shift as follows. You apply this shift to your function g and take the value at 0, or just in other words, for a basic shift for monomial of formed by shifts, you just take the value of g in the corresponding point. All right, and one more thing is that all algebras, so let me say it, let A be a commutative algebra generated by certain elements. Well, so this I'm going to put just A here. So with the Gorenstein duality pairing, then this algebra is isomorphic to the algebra of shifts for the following function, having an element k of my lattice. I take my generators to the power k1, etc., ks, and I apply my linear form to this operator. I get a function, and this function will be exactly the function such that if you mod out the shifts by the annihilator, you'll get this algebra A. Okay, and so as I mentioned, if G is a polynomial, then you get finite dimensional algebra. But if your G is arbitrary, well, you can easily find examples when the annihilator is 0. So let's take double exponent. It grows too rapidly. And so then its annihilator will be 0. Right. Okay. And I'm going to apply this to K-theory of toric varieties. And well, let me take a smooth toric variety. And well, having a smooth variety, I can define it's K upper knot. These are vector bundles on X modulo the following equivalence, that if I take a short exact sequence of vector bundles, then the middle term is equal to the sum of the first and the last terms. So I take a free abelian group generated by, or just vector space. Maybe I prefer to work over Q. This doesn't matter much actually. So I take a vector space generated by these guys and I mod it out by this relation. Or I can do the same for coherent sheaves and get what is usually called K lower 0. But for smooth varieties, these guys are the same. So I'll refer to them as just as to K of X. And standard fact is that, well, for a smooth toric variety, its K-theory is an algebra with a Gorenstein duality pairing obtained by taking the, well, to multiply two vector bundles, you need to take their tensor product and take its other characteristic. Okay, and well, as usual, everything is generated by T equivariant line bundles. So they play the role of divisors in this case. So K-theory looks very much like the cohomology theory, but there's no grading. Instead, there is a filtration. So having a line bundle, which is of sum of di's with certain coefficients. Again, I can take a virtual polytope defined by these numbers. And if my numbers are integers, and so I get a polytope in a lattice, well, suppose I get an actual polytope. I can count the number of points, of integer points of this polytope. And a standard fact from, I don't know, from geometry said that the number of such integer points is a polynomial in H's, and it's usually called the Ehrhart polynomial of this polytope, or maybe of its normal fan instead. So, and you see, it's very close to the volume polynomial, but still different. So suppose you have a, I don't know, if you have a triangle with side of length x, where x is integer. So the number of integer points is what? It's 1, 2 plus etc. plus x. So this is x plus 1 over 2. And the volume of such a thing, oh yeah, that's right. And the volume of such a thing is just x squared over 2. So you see that this thing is not homogeneous as opposed to volume, and but its highest term coincides with the volume polynomial. So this is the volume polynomial plus certain junk. So, and a theorem, well, a standard theorem which you can find in any textbook in toric varieties, says that the Euler characteristic of a line bundle is equal to the number of integer points in the corresponding polynomial. So to the value of the Ehrhart in the corresponding polytopes. So to the number of points in the delta H, which is the Ehrhart polynomial corresponding to H's. So, well, if we apply our result to this construction, then we get a description of the K-theory ring of Y sigma. So this is the algebra of shifts on the lattice of integer virtual polytopes. So the coordinates need to be integer with a given fan, modulo the annihilator of the Ehrhart polynomial. Right. So, and this theorem you can use to actually to make some computations in K-theory just by looking at a polytope and considering its faces and intersecting them and computing the number of points. So let me briefly comment on that. So in K-theory, I can write some special classes. So for instance, I have line bundles, which are of this form, and to them I can assign in my ring, I can assign the monomials corresponding to shifts by, well, not monomials, just linear functions, shifts by some vectors. So, and what corresponds to structure shifts of orbit closures. So O sub di is 1 minus the shift. So if I take a polynomial, if I take a polytope, let's say P, which is drawn in blue here, and if I shift one of its facets just by 1, and if I subtract the smaller polytope, well, the number of integer points is, well, it's more or less the number of integer points in this facet. Well, it's the number of integer points in this facet of this red polytope. And what if you multiply several operators of this form? You get faces of smaller dimension, which are just intersections of the corresponding facets. And that's how you get the structure shapes of Q-orbit closures. And in particular, if this product, well, if these faces do not intersect, so this product must be 0 in my ring. So I get relations in the K-theory. So there are two parts of, well, there are two classes of relations. Namely, what can I do to a polynomial to preserve the number of points? Well, I can shift the whole thing by some integer vector. So by parallel translation, I'll certainly preserve the number of points. And this means that the Ehrhart polynomial of d plus x is the same as the Ehrhart polynomial of delta. So this element 1 minus the product of the corresponding shifts lies in the annihilator. And then the second series of relations, as I mentioned, is obtained from collections of rays not forming a cone. If they do not form a cone, I get something in the annihilator. Okay, and well, this is not quite well, I mean, this is just a new viewpoint on some known stuff. I mean, the K-theory of a toric variety was described in various papers, but I think we get a new look on this and, well, some new viewpoint, and that's kind of funny. But what I want to say in the remaining 2 minutes is that the same machinery can, both in the cohomology and K-theory case, can be applied to flag varieties as well, to the flag varieties of type A. And for flag varieties, well, I'll be very brief in this part. You need to take the Gelfand-Zetlin polytope, which is defined by a bunch of inequalities. So you need to take a triangle table. You form, you fix some initial values, lambdas, and then you take inequalities defined by this triangle table, and so on and so forth. You get a polynomial, you get a polytope. Well, for 3 dimensions, it's written here, and in 6 dimensions, I cannot draw it. So its volume is the van der Monde determinant, and the Ehrhart polynomial is just a shifted van der Monde. So this reminds you of the Weil dimension formula, and in fact, it is the Weil dimension formula. So you can play the same game with various differences that on this polytope, you can take the ring of differential operators, take the annihilator of the volume polytope, and get the homology ring of G mod B. And this is my classical result due to Borel, and in this setting it was observed by Kiumars Kaveh. And our observation is that our construction gives you the K-theory of G mod B. And if you're interested in doing intersection theory, you can find explicit representatives of Schubert varieties in K star of G mod B. This was done by Valentina, Kiritchenko, Leonid Monin, and myself in 2012 in the cohomology ring. And also you can take representatives of structure sheaves of Schubert varieties in K-theory. And this is our recent result with Leonid Monin. Well, I think I'm already 1 minute out of time, so thank you.
Thank you. Very good.
Thank you.
Женя, I have a very general question. If
Sure.
there exists a non-commutative generalization of such kind of rings, and if it is, do they play an important role in geometric structures? I mean, if you consider the differential operators with the non-constant coefficients, or something more general like Drinfeld double and etc.
I don't know. This is wide open. I was thinking about considering differential operators with arbitrary coefficients, but you get something like really huge. What I can do instead is that I was considering all the story over a field or over Z. I can take the Laurent polynomials on my torus, so functions on my torus, and do everything over this ring and get the equivariant cohomology of equivariant cohomology and equivariant K-theory. And I don't know, maybe quantum K-theory is somewhere nearby. I don't know. This is really interesting. I hope you can say something about the quantum cohomology. Well, small quantum cohomology of flags. This is pretty much well understood.
Other questions? If not, Jane, thank you very much once again, and see you.
Thank you, and I'll be glad to come to Yaroslav in person. Okay, thank you very much.
Thank you. Bye bye.
Thanks everyone. Bye bye.